Okay, so hello. Thanks for the introduction. So we'll talk about the dynamic bus scheduling problem. It's a much lower level talk than the previous two. I'm still talking about public transit, but I'm looking on a very specific stage of its planning and in a different context than the context that Itik did. I'm looking on public transportation in low demand area, in rural area or small towns. It's a joint work with Ilit, Oppenheim, who is here, and it's also started as a joint ISTRC research with ISTRC funded research with the late Yuval Adas that was mentioned here at the beginning of this talk, and we all very sad about his losses. Yeah. So this is the outline, but let's go inside. So providing efficient public transit service in rural area is challenging, where the demand is low. We're not talking about high frequency line, but on schedule lines. And in practice, if you look at least on the public transit system in Israel, in many areas in Israel, buses are traveling almost empty, sometimes even really empty. Some trips, only the driver is there. And several years ago, a guy called Yuda Pua worked for in Ashiloach journal, Hebrew journal for economic, I would say economic libertarian thinking, check the data and state that almost 600 lines in Israel are actually traveling with an average, at least some of their trips throughout the day are traveling with an average occupancy of less than one passenger per trip. And of course, it's the extreme edge of the vicious cycle problem. We have a service which is low frequency, not provided very well. Variability is very high, and it's very hard to provide good service because there is no good service in this area. People depends on private transportation, and nobody use buses unless they really have no other alternative. Now, one direction here is to look on a fully flexible mobility on demand. That was also mentioned a lot here. And there were several attempts. There is even one which is still ongoing in McHefer. And the problem, well, there are some sweet spots for mobility on demand, and I also looking on them. Maybe it will also be reflected in other presentation here. But in general, mobility on demand is not a perfect solution, especially not for a low demand area. The advantage of fixed line is that they are attracting demand. There is a line, people with fixed line and fixed route and fixed schedule, and people adapt their activities. And in the long run, they may even adapt their way of life. They choose their residential location and workplace according to the supply of transportation. Now, once you give them the opportunity to open their smartphone and order a vehicle that's supposed to take them from A to B, whatever A and B are, and at what time they want, so you lose this consolidation effect. You will find, again, vehicles that are traveling completely empty, and we saw many such mobility on demand initiative failed because of a very low fill rate. So our research was started with collaboration with an Israeli startup company called Operati that was founded by this guy, Israel Rom, who could not be here today. And he used to be the senior information system manager director of Eged for years before retired and founded this idea. So he's a public transportation fixed line guy, and he said, okay, let's try to come out with this idea of providing a public transit service to low demand area. We stick with the fixed route and fixed schedule as we are doing today, but we will change the way that people are boarding on this bus. So you cannot just walk in a bus, wait at the bus stop and walk on the bus. You have to submit a trip request before you do it. So you can request a trip that is planned, that is on the schedule according to the line, but you have to request it sometime in advance. Again, it could be using a mobile app with the same experience as you have with mobility on demand services, but unlike mobility on demand, you are restricted to the schedule and the line that are planned and exist. The fleet that will serve this will be heterogeneous, meaning that it will consist of vehicles of various size. Some of them will be small vans, some of them will be minibuses and buses, and perhaps we will also use taxis for some of the trips. The allocation of or the assignment of vehicles to trips will be done in real time. So short time before the trip, we will assign the vehicle based on the demand that was accumulated, based on the requests. And trips with no request at all will be cancelled. At least the idea of Israel Roman, we have to check whether it is a good idea, is that all journey requests will be met. So even if there is only one request, we will send a vehicle to serve this trip. So the experience from the passenger point of view is like fixed line. If you want to travel, we will provide it to you. But if nobody wants to travel, we will not dispatch any vehicle. And also, he said that I'm not sure that tariffs is a big issue in public transportation. In Israel, they are very low anyway. But the idea is not to change the tariff. So it's not like the mobility on demand that people it's considered a premium service and people are paying more. Now, the pros of this idea are clear. You can save costs because you're using smaller vehicles and some trips are canceled. You can reduce externalities. We use smaller vehicles, so we produce less pollution, less risk of accidents, noise. And especially in rural area, this can be significant because people don't like a huge empty bus passing along next to their inside their village a few times a day. And another side effect is that we can collect data very, very efficiently and accurately because we know exactly from where to where people are planning to and actually traveling. Yeah, the cons though are that we are asking ourselves, will passengers agree to this arrangement? Will they accept this idea of, instead of walking in a bus, having to plan their trip in advance? And recall that I'm talking about a scheduled service. It's not like line number 5 in Tel Aviv that passes every 5 minutes and you just can go out to the road and take it. So we're talking about relatively low frequency lines. So it makes sense that people do plan because they have to adjust themselves to the schedule. From the operator point of view, the planning is harder. A public transit provider, at least in Israel, they use quite low-tech tools to do their vehicle scheduling, and it's very convenient to them that the same trip is served by the same vehicle every day, sometimes or same type of vehicle at least, sometimes for year. And in here we need to make an online decision, and the question, can we do it, and can we do it efficiently? And of course, there are also regulatory barriers. You cannot just switch to this mode. You need the Ministry of Transportation approve it. It's not compatible with the current regulation. And then there is the question, is it worth it? Can we really, is there money on the table here? Can we save, can we really, is the saving is really significant? Regarding the passenger acceptance, a study that runs in parallel to this study was led by Ilit with Sapir Moalem, a student, MSc student from Tel Aviv University, who checked this using both quantitative and qualitative surveys. I'm running out of time, so I'll not go into all the details here, but the bottom line of this study was that overall there is a positive attitude of passengers, of relevant passengers toward this technology. Passengers do realize that it doesn't make sense that buses are traveling empty, and this passenger aware of this. They would expect, they're afraid from technical issues, so they would expect technical support, and they testify that whether this will be accepted by their peers will also influence their acceptance. In a free text thematic analysis of their answers, we also derive several observations regarding the features that passengers are expecting from such a system, such an app. And many of them are actually inspired by what their people are expecting to get from mobility of demand transportation apps, including some information about delays, about the location of the vehicle, who is the driver, and so on. And there are other observations about public transit. So we are going to focus, as I said, about the dispatching problem. How we dispatch, how we assign vehicles to trips. And this is an old problem. In the static setting, it has been studied for many decades. And here are two surveys about this problem. One of them is in Avishai Sider book. More recent study focused on new technology, mainly about battery electric vehicles, where you have to schedule the vehicles and scheduling their charging simultaneously. We also see some studies that look on the robustness of this system. What happens if there are delays due to problem in the traffic? So this is another kind of dynamism. It's not related to the demand, but it's related to other random effects. And as much as we look for, we couldn't find any bus scheduling literature that focus on dynamic demand and on decisions that are made online based on the demand. So let's define the dynamic scheduling problem, but let's start with an easier version of the problem, assuming that at the beginning of your planning horizon, and planning horizon now is short, let's say it's 1 day, you have all the requests submitted in advance. So in this case, we have to schedule the vehicles. We have to decide which type of vehicle is going to serve each of the trips. In this model, we assume that all the vehicles are routed from the same depot. They're all. We're talking about what we have in mind is a central station of a rural area. Of, let's say, our use case is Carmiel. Several lines are departing from there and returning for them, and each trip is a round trip. Each trip is something that go perhaps back and forth, but so decisions about the trips are made in the same place. And this means that we are restricting our attention to the scheduling issue. The spatial issue became simpler. We just, whenever a trip starts, we have to say which vehicle, which is now available at the depot, is going to serve the trip. it may be even more than one vehicle. We may have in our available fleet now vehicles that are too small to serve all the passengers, so we may send, in some extreme cases, more than one vehicle. And the objective will be on the short run to minimize the total variable cost. So there is a cost associated with operating each type of vehicle based on operation time. The fleet is already there, so we already paid for this, and we are only interested in the variable cost. We formulate this problem as a linear integer program. The decision here, marked in blue, is a decision variable xij. It's how many vehicles of type I are going to serve trip j. So actually, we don't care about the lines. We just have a list of trips. Each trip start and end at the same depot. We just need to say which vehicle serving each trip. And recall that we know how many passengers we are going to have on each trip. So the objective function is to minimize the total cost. So PPI is the cost per hour for vehicle type I, and TJ is the length of trip in hours of trip J. And we just minimize the total sum, subject to constraint. The first constraint is that each trip is served by vehicles with total capacity that is greater or equal to the number of passengers that request this trip. And the second constraint is that says that the number of vehicles that are on duty at each point, actually at each departure time, which is enough, would be less than or equal to the number of vehicles that we have in our fleet, which is given for now. So theoretically speaking, this is an NP-hard problem, and it's potentially could be hard to solve, but for any relevant side, and I'm talking about instances with hundreds of trips per day, we can solve this problem in a fraction of seconds, less than a second. So it's something that we could solve very easily, but for now it's not completely dynamic, this problem. It's something that we need to solve only once a day. Now, reality is a bit more complicated. We cannot expect all the requests to be submitted a day in advance. We may expect the passenger to submit the request an hour or half an hour or a few minutes before the trip departs, but not all of the passenger will be able to know about their planned trips and plan them a long time in advance. So our idea is to solve this model using a rolling horizon framework. We are going to solve it repeatedly every time one trip, or perhaps several trips at the same time, are about to start. And we will solve it with all the vehicles that are already out, taken into account. We know about the demand of the current trips, because they were already submitted, and we have a forecast, we have an estimation of future trips. So we solve the problem every time a trip is about to start. As I said, we can do it very quickly, but the idea is that we solve it based on an estimation, and we update our estimation continuously throughout the day. So the estimation is also updated based on requests that were accepted and based on other information. So this is about dispatching the vehicle, but people are actually solving bus scheduling problem also to answer a strategic question: how many buses do I need? And in our cases, it's even more complicated because we have several types of vehicles. So how many buses do we need to provide the service over now a longer planning period, say a year or several years of each type? So in the static problem, it's relatively simple. Once we solve the bus schedule, 10 minutes? 5, oh. Okay. In the static case, once we solve the bus scheduling, we can derive the exact number of vehicles that we need. But in our case, because demand is going to change over time, we have to take these changes into account. So Okay, so the idea, and I will not get into the details of this model, is that we can solve it based on a set of estimated future scenarios that we can deduce from historical data. And then we need to make the assignment over all the scenarios using the same fleet, and we are minimizing both the variable and the fixed cost of maintaining the fleet. We are going to compare these results to what we can get from a static fleet. The same vehicles, still an heterogeneous fleet, optimized heterogeneous fleet, but the same vehicle must serve each trip every day, as it is done now by all of the operators, at least in Israel. So we wanted to test this with real data. We look on a set of 5 lines that are departing from Carmiel and returning to them. These are the lines. These are not good candidates for being ghost lines. These are actually lines that works with 191 trips a day in total. So in the peak hour, they do several trips an hour, but not every 5 minutes like in Tel Aviv. We collected data from 231 regular working days after getting grid, cleaning some overlays from the passenger counting data published by the Ministry of Transportation. Overall, the average ridership in these trips was 3,500 passengers a day. So you see that on average, it's almost 20 passengers a line, but the variability is very large. And we also conducted sensitivity analysis by shrinking and inflating this demand in the range of 50% to 200%. There was some issue with the data, which I don't have time to get into. We postulate a fleet that consists of vans, minibus, and buses, as listed here. And we also allowed using taxi, which are not owned by the operator, so we have to pay for it only the variable cost, that of course tend to be higher. And if you have better number than this, I would be really glad to hear about this. So this is the comparison between what we can get from static assignment of the buses and over the same set of scenarios, the same set of 231 scenarios, but we didn't build the static assignment of bus to be able to serve all the passenger, but only to serve either 95 or 99%, all the passengers in 99 or 95% of the trips. And you see that the cost would be, for our baseline, 3,500 passengers, would be about 70 to 75 shekels a day. So this is many millions of shekels a year to serve these lines. And now, if you do dynamic vehicle assignment and you make our optimistic assumption that you know about all the passenger in advance, you can save more than 20% out of this cost. But in reality, you don't have it. So we are working now on devising forecasting mechanism, but for now, we only assign the buses dynamically but greedily. At each trip, out of the available vehicles, we selected those that will minimize the current trip only. And this is already, as you can see, make most of the possible saving. So we can improve between these dashed and solid blue lines, but not that much. This is the cost per passengers. This is the optimal composition of the fleet, which, as you can see in the dynamic case, consists of a bit fewer vehicles and much smaller vehicles. So indeed, much smaller vehicles are actually traveling. The taxis are used but very seldom. So to wrap up, we believe that there is an opportunity for significant cost saving and externality saving in providing public transit in this area. The models are really simple and easy to solve, especially our greedy one. I'm happy one. And perhaps if we want, we can use this saving. If we have a budget for providing this public transit service, we can use it to improve the service. For example, to increase the frequency, at least the potential frequency. Maybe some of the lines will not be served. Passenger acceptance is likely. People, and it's also supported by results that Operati collected independently. There is interest from municipality and public transit operators. Many of them contacted Operati, but government action is needed here, regulation and possibly supporting a pilot project. There are many venues for future research, which I will be happy to discuss with you in the break. I hope that I left some time for questions. Thank you.
We have time for any questions. Okay.
Yes, please. Very good presentation and an excellent idea, and I really like what you're doing. The quality of your evaluation is based on the accuracy of the scenario. In principle, if the scenarios that you're using and the scenarios that materialize are somewhat different, then your evaluation may be slightly off. You
are right. You are right, and we are aware of this. One of the experiments that are running now is to try to make the planning based on a training set and then test the scenario using a different set. I don't have the results yet, but I want to comment in this context that also the planning for the static lines was done based on the same scenario, and the evaluation was done. So the comparison is fair. Yeah, that's true, but their ability to satisfy the demand will be reduced because you are planning based on past scenario, and in the future you may have different demands. Good point, though. Yeah, it's
usually people discuss cancellation of line, especially in the rural areas. There is the cost of the line, the support of the line. Let's spend this money for taxes for those few users. And when this threshold will be passed, we will bring back the line. So, and it fails to be realized by many administrative reasons. So, can it be the first step? Or is this more complicated?
You mean the first step would be to just cancel the line or to just cancel trips?
And spend the budget of the line for the taxes. So it's very simplified version of what
what do you mean for the taxis or for the tax?
Taxes of the same people. There are 5 users an hour. Support the line costs much more than 5 XC.
Yeah, so this will be happen here automatically because one of the vehicles in our trip is a third-party taxi. So some of them will be used, but at least using my evaluation of operational and fixed variable and fixed costs, the taxis are not, and in this context, maybe in more deserted, less populated area, the situation will be different. Taxis are not used much. They used in few times a day out of the 191 trips a day. So yes, this is something which is built in here. If you have lines which are not with a very small demand, and if you do not have your small vans available, which would be cheaper for you to operate if you already bought them, then you would use taxis. And it will happen within this model. I hope it's answered your question. Okay. Okay, I will be happy to. Let's talk about it. Thank you.